So now we're going to be talking about global circulations of water. So in talking about water, we're talking about another fluid, much like air is a fluid that flows. Of course, water is too. So it's subject to the same horizontal and vertical structures that impact air, even more so. So we are going to be talking about the vertical movement of water first. The vertical movement is measured by sea surface temperature, SST, and we're going to use the specific examples of the California current and the Beru-Humboldt current off of South America. So let's get to it. When we talk about each of these currents, they have something in common, and that something is a phenomena called upwelling. Now, upwelling is an outgrowth of the Coriolis effect on water. Let's go back to the Coriolis effect first. The Coriolis effect impacts currents as well as it impacts air. And in the case of the California current, there is a current that comes down along the coast of California from the polar regions that is a cold current that is running from the north to the south. It's in the northern hemisphere, so you know that the Coriolis will deflect it to the right. So this particular current is really noted when it is backed against a landmass. And then you really start to notice the current heading to the right. So you see this coming down and deflecting to the right, deflecting to the Western Pacific. When it comes to the Beru-Humboldt current in the southern hemisphere, this current will also head from the polar regions around Antarctica toward the equator. So it is heading from the south to the north, but it is the same kind of cold current as the California current. And as it heads in that direction, it is going to deflect to the left because it is in the southern hemisphere. So we've talked about how the Coriolis effect impacts ocean currents. Now we're going to talk about this phenomena called upwelling, which is added to it. Upwelling is a way to replace the water that is taken away from the area where the deflection really takes place. So we have a current coming down, bringing water molecules with it. Suddenly it deflects to the right, and it leaves an absence of water molecules here. As a result of this, upwelling brings up the cold water from the depths to fill that void. Now, it's a pretty unique way to provide equilibrium in that area, equilibrium of mass. When this mass was reduced by the molecules moving to the right, suddenly you're not taking from warm to cold and filling the equilibrium. You're actually dragging up water from the depths to replace it. So upwelling is definitely a physics phenomena in moving this water up from the depths of the ocean. And you may doubt that it happens, but we have some satellite evidence for you. And this shows the California current that is coming south and is against the land mass north of San Francisco. And you see here that this is deflecting to the right. Look, you can even see it deflecting to the right. And as it's deflecting to the right and moving so many more water molecules to the right, this upwelling is very cold water. It's 10 degrees Celsius below the actually it's 10 degrees Celsius water, very cold water in the 40s, that is being pulled up from the lower ocean to replace what is being lost. That's why surfers out on the West Coast in the middle of the summer will always be wearing wetsuits, because they really face these cold temperatures coming up with the upwelling surfaces. Conversely, this is the Peru-Humboldt current. This current comes from the South Pole up toward the equator, and this current is backed up against a landmass that really accentuates the left-hand pull of the Coriolis. And when those water molecules head to the left and head to the Western Pacific, this cold water from underneath upwells up and replaces it. You're seeing all the cold water that's in there as well. So upwelling is a phenomena that we can study, that we can see, that we can measure. And in a normal year, and what I'm saying is a normal year is a year without El Nino or La Nina. And I know you've heard of El Nino. We're going to study that in a second. But in a year that is neutral, a normal year, like in 1993, this is the ocean temperatures that you'll be finding across the different latitudes. And you will see here that the cooler temperatures for the ocean are the more blue temperatures. And you will see that the upwelling is bringing cooling temperatures off of the California coast, and it's bringing cooling temperatures off of the South American coast as well. And there's an area in here that seems warmer, the yellow area. Let's go explore that. This is a neutral year right now that I'm showing to you. And it's still rather warm along the equator, which makes sense because the equator is so warm. Let's look into the physics of it a little bit more. Those cold sea temperatures that I told you about for the California current and the Peru-Humboldt current actually produce really dense air right in the surface over the ocean and contribute to surface highs in this area. So remember, temperature always drives pressure because temperature predicts how dense or how buoyant something will be. These cold areas off these coasts produce dense air and surface highs. A surface high in the Pacific in the southern hemisphere and a surface high in the Pacific in the northern hemisphere. And every 5 to 7 years, this pull of water and this upwelling of water contributes to an actual difference in the sea level height in this Western Pacific area. So consider the fact that both of these currents are heading toward the Western Pacific. The Peru-Humboldt current is heading to the Western Pacific with its upwelled water. The California current is deflecting to the Western Pacific with its upwelled water. The Western Pacific and Indonesia actually can record higher sea levels of about 1.5 inches to 2 inches in some years. Well, that is a situation that cannot be sustainable. It's certainly not an equilibrium situation. And as a result of that, every 5 to 7 years on an irregular basis, these pressures, these high pressures here and the high pressures here and the inflow of water to the Western Pacific will all flip around and equilibrate. That flipping process is known as the Southern Oscillation. The reason it's known as the Southern Oscillation is because this happens really just south of the equator. The California current adds to it, but most of it is south of the equator and known as the Southern Oscillation that really impacts Indonesia. Let's explore it a bit more. Normally, a January cross-section of the ocean from Peru to the Western Pacific shows that there is a high off of Peru, like we explained. And this is driving, along with the upwelling, this water and temperature over to the Western Pacific. You might note that this water can be cooler, but remember, it's right along the equator, so it is warming. And we are in January at the southern summer, so it's warming quite a bit. So warm water is heading to the Pacific, which is causing warmth over the Western Pacific. And remember, rising slow, clouds and snow, surface low. There is a surface low in normal Januaries over the Western Pacific. There is cold air upwelling up, and this is known as a thermocline. The Western Pacific has more warm water. The Eastern Pacific has less warm water because you're pulling up so much with the thermocline. Let's keep going. Oh, we'll do that on the next slide. We'll get to El Nino and La Nina next. See you there.